All right, okay. In this video, we are going to be looking at temperature, eventually leading to how temperature and energy are related. So temperature is just a measurement of a property of a material. So we could use, if you imagine the standard thermometer, for example, that is a temperature scale measurement based on the expansion of a liquid inside here. Now, we use mercury, obviously not anymore because it's toxic, but sometimes we use an alcohol. And it's the property that this liquid expands when heated that we're measuring and we're using as an indicator for what the temperature is. So we're just using a property, and that property used in this case is the expansion. When heated. And you can use any number of properties that change when heated. So, you know, in the example of a thermocouple we'll look at in lesson, like two pieces of wire kind of wound together, give you a thermocouple, and we'll look at the properties, how the properties of those metals change when heated up, and we then use that with a voltmeter to work out give us a value of temperature in this case. So, but for the most part, we measure temperature with a unit. We have the unit 0 or in degrees Celsius, or we might use the value of Kelvin. One thing you need to be aware of is that the difference of Kelvin and Celsius is exactly the same. So 1 degree of Celsius is the same as 1 degree of Kelvin. However, in terms of an absolute value, this is for changes. So if you have a change of 1 degree Celsius, it's the same as a change in 1 Kelvin. But absolutely, for example, we could give some examples of how we use the conversion between the Celsius and Kelvin, which you will need to use this conversion, which is the fact that we appreciate that 0 degrees Kelvin is equal to minus 273 degrees Celsius. They are the same value, or what we call thermodynamic temperature. Okay, those are the same thermodynamic temperature. So so the Kelvin scale is what we call a thermodynamic temperature, whereas this is based on, we normally measure temperature in terms of a property. This is based on ideal gases. And we'll come to ideal gases later on. We'll have a look at what ideal gases are, and the fact that where we get this 0 Kelvin, negative 273 from. And you can use this as a conversion. This is absolute 0. You can't get negative Kelvin, so just bear in mind that. So this is the absolute theoretical temperature. I mean, it's a very theoretical value. So minus 273. And just to remember that 1 change in degrees Celsius is the same as 1 change in degree Kelvin. So what is temperature then? Well, what is it? Now, some people like to say it's an indication of the amount of energy, and you wouldn't necessarily be wrong when you say that, but actually it shows temperature allows you to give an indication of the direction of the energy will flow. So say, for example, if something has a lower temperature than the surroundings, then energy is going to flow into it. So energy flows into it. Whereas if we have a higher temperature than the surroundings, if the temperature is higher of an object than the surroundings, then energy is going to flow from that object into its surroundings. So temperature allows us to indicate a direction of energy flow. So temperature indicates a direction of energy flow. And like I said here, when something is lower temperature than its surroundings, then it's going to take energy in. Okay, that energy is going to be transferred in. And when we have a higher temperature object, that's going to give energy out. So that's what temperature does. It indicates the direction of energy flow in this case, which obviously has its uses in many places. So it is to do with energy, and the energy in this case is flowing from one place to another based on the temperature. Okay, so temperature just gives an indication of the direction of energy flow relative to another object or another situation. But what is then, so that kind of leads us to our next kind of point. What is the energy that the heat energy that something has? Okay, because obviously it's related to the temperature, because if it's got a lower temperature, that means it's not got as much energy as the surroundings. So what kind of energy is it going to gain? We call this this energy internal energy. So we have this idea of internal energy here. So let's write this idea of internal energy. And so the internal energy that something has would obviously give rise to a temperature. And the internal energy is defined as the sum of potential, I can't write apparently, potential and kinetic energy of a substance. So it's the sum of potential and kinetic energy of a substance, okay? So it's made up of a set of potential and kinetic energies. And actually we can discuss the difference between potential and kinetic in terms of, you know, what they actually are. What potential energy is potential to do something, and the kinetic energy is the movement energy, how much movement it's got in it. So that gives you an idea about what the internal energy is in this case. Now, we'll talk more about the energy that something has or the energy that is transferred, because we have a couple of equations that we need to know about energy transfer. So let's start with the most obvious one, which is Q is equal to mc delta T. Now, you may have come across this equation before. This is the equation utilizing the specific heat capacity. And later on my channel, you'll see me do some questions on this. I really would watch those questions that utilize specific heat capacity. And the other equation here, which is the latent heat. So the latent heat. So which is Q is equal to mL. Let's just chat about these two equations. So this is the latent heat. Now this could be, there's two different values that this could be. And I'm going to draw a graph here in a second to just describe what the latent heat, or a sketch graph even, just to describe what the latent heat actually is in this case. I'm just looking for some different colors here. Oh, there we go. So the latent heat in this case, let's see if this green's working better. It is. Wow, that's much nicer. Okay, so we've got our latent heat. Now, like I said, there's two types of latent heat. We've got latent heat of fusion, and we've got latent heat of vaporization. Vaporization. Sorry, my spelling is bad. Vaporization. And actually, these words do give an indication as to what that's for. Now, in each of these different situations, each equation is utilized, suggests how this energy that's either been taken in or given out is being used. So how is that energy being used? So when I said, it showed you before, and I said that heat was either taken in, energy was either taken in, or energy was given out based on the temperature of the object. Well, what is that energy then used to do? Okay, and actually that's where potential energy and kinetic energy comes together. In terms of which one is being affected in each case. So in this case here, we have, this is all about, and this gives you an indication, this is the amount of change in temperature. So this equation is all about the energy being used to change its temperature. So the energy in this case is being used, energy used to change the temperature. So the energy is being used to change the temperature in this case. Okay. What about the other equation? Well, the other equation is where energy is being used. Energy used to change state. So the energy in this case is being used to change state. And this actually gives rise to why we have two different values, because as you well know that there is solid, liquid, and gas. So depending on the state change that you're using, depends on which value of latent heat, which these are constants, specific heat capacity and latent heat are constants for the materials that you're using. And so the latent heat of fusion is all to do with from solid to liquid, and obviously back, because, and the reason I say it could be back is because remember, you can either give energy, take energy in, or you can give energy out. So if you're taking energy in, you're going from a solid to a liquid because it's gaining energy, isn't it? But if it's losing energy, well, then it'll be going from a liquid to a solid. Same with vaporization, just of different states. So we have liquid to a gas. And like I said, the word does give the idea, the vaporization is being vaporized. But again, it can go backwards and forwards. It's the same, it's the energy in this case that's being used to change state from gas to liquid or liquid to gas based on whether it's being taken in or given out. Okay, so it would lose energy, it would be giving out energy if it was turning from a gas to a liquid in this case. Well, now there's more to say about this latent heat equation because one of the things that's very, very pertinent is actually when we look at a graph of the temperature of an object or of a, say, a substance. We'll talk about what substance this could be in a second, against time. And this is a very common graph that people like to show. And usually this graph looks something like this. It goes like this. Now, actually, this graph could be drawn the other way around as well. There's no reason why it can't be drawn the other way around going down. And I'll explain why that is in a minute. But in the case of this one here, we've got a pen that works. In the case of this graph here, this is showing how the temperature changes with time. Now you can actually do this experiment in class, and we probably will do, just to show and draw this graph. It's very, very nice observational, simple observation, really. So say, for example, we start with ice. We start with ice. So this is ice at, you know, we'll probably have to make this negative. So we'll say maybe it starts at maybe negative 5 degrees or something like that. It doesn't matter. I haven't put the x-axis in the right place, but you'll forgive me for that, I'm sure. So as the temperature increases, the temperature of the ice increases. So which equation is being utilized here? Well, which equation is being utilized is this one, because there's a change in temperature. So here, this is energy is being used to change the temperature. So the energy that's being given into heating this ice is being used to change the temperature. Now look what happens next. We have this flat line. Well, what is that telling you? It means over time, we're not getting any change in temperature because we've got a flat line. Well, that's interesting, because obviously we're heating up this ice and we're assuming that we're still heating up this ice. So why is it not increasing in temperature? Well, it's not increasing in temperature because the energy is not being used to change the temperature, it's being used to change state. So here we've got our first change of state. We have our change from solid to liquid. So over the course of this process, all the ice is melting and the energy is being used to turn it into a liquid. So now let's have a look at the next section. So what's happening now? Well, after it's all been turned into liquid at this point, we'd assume all of it's been turned into liquid. And then so the temperature starts to rise again because we're using this equation here. So the temperature rises, it rises until it hits the boiling point. And so as a result, what then happens is it's going to go from a liquid to a gas. And exactly the same thing is happening here. So again, because we're giving it energy, but we are not changing the temperature, that means that there is no change of temperature because we are changing state. The energy is being used to change the state from liquid to gas. So we're putting energy into this situation. So in this situation, we've got our boiling point, and I'll just put BP there, and I'll actually put the melting point in. I didn't actually spot that before, but we've got our melting point and boiling point for liquid to gas. So quite nicely here, and then you could extend this graph further because then obviously you keep heating the gas and that would keep heating up the same as before. Now, obviously I've kind of just sketched these lines. The steepness of this is an indication of how much temperature you're getting for the energy that's being transferred in this case. Now, obviously, the gradient of this line would be an indicator of, how effective this was at changing the temperature, how effective the material was. But you can look at the kind of ins and outs of that when we see questions on it. But yeah, so this is really nice to observe that when we see a flat line on a temperature time graph, this is where there is a change of state occurring because the energy is being used to change the state, not change the temperature. So which equation would you use? You would use this one for a change of state and this one for a change in temperature. Some of the things I didn't mention about these specific heat capacities, such as the units. So you can find out the units for these. I think it would be interesting for you to kind of have a look at this, or interesting to know what these units are. The latent heat in each case. You do it by rearranging these equations. So Q, in this case, you've got Q over M delta T. So it's the energy per unit. So I'll let you work that. I'll let you write in for your own notes here. That'll be a little question I can ask you when we get into class. But you've got energy measured in joules, mass measured in kilograms, temperature measured in Kelvin or degrees Celsius in this case. I'm not too bothered. And then this one is a bit easier because rearranging for L to find the unit is joules and kilograms. So that one's quite nice and easy. You should be able to work out that unit without too much difficulty. So yeah, so have a look at what you think the units are for those, and we'll come back to those in class. Other than that, I think we'll leave it there with those equations because I think this is a good place to stop. And next, you'll have a look at the videos that show kind of some examples of how these equations are used, and that will give you a nice kind of indication as to the challenge that utilizing both of these equations often can actually present to you. Okay, till next time.